Hello everyone, this is Ray Long, and welcome to an episode here, our first episode in fact, of Full Stack Distributed Systems. Today we're going to be showing you a little tiny small program in C. This is kind of a throwback to the classic era of software development. C is one of the first really important modern-ish languages that has come about in the past, 40, 50 years, 50 years of computing. So C is a very powerful language, very small language, very close to the machine, very close to the metal. Some would call it a very low-level, high-level language, or a very high-level, low-level language. The point is, it's got a very small amount of features, and it's very close to the machine. So we're going to go ahead and take a look in CLion at a project that I put together here, just to kind of walk us through some of the features of modern C development. So if you've used a JetBrains product before, this might look familiar. This is a JetBrains IDE called called CLion, which is based off of IntelliJ. And you'll see here that the project's not very big at all. This is it. This is everything. Let's take a look at the README. Alright, so IntelliJ is showing us that we have plugins that'll help us manage Markdown files. So let's go ahead and install one. Let's see, the JetBrains one. Yeah, I typically like the JetBrains plugin for Markdown. I don't know, just my style. Alright. I literally just installed CLion right before I started recording this video here. So, alright, so we have... Why don't we go ahead and restart that later. For now, we can just take a look, and we'll see in the README, it's just a tiny repo to familiarize myself with the C programming language, specifically C99. What is C99? Well, it's the 1999 official C language specification. So let's take a look at our main C file. Let's just jump right into it. There's not much code here at all, really. Two files of code, main.c and user.c. So main.c, we have some fairly standard operations here going on at the top of our source. We see some include statements. We'll be including a couple of libraries. We have standard IO and standard int. And we're also going to be including a custom file called user.c, which we can see highlighted over here. Right? We'll get to that in a moment. The first thing we're going to do is we're just going to define a very simple function. It's going to return nothing. That's why it's called void. In C, the first word when you define a function is the return type. So this returns nothing. So we're going to call it void. Okay, so void some other work. And it's just going to print a statement. It's just me doing some work. We have this function here called inline demo. This has a bit of sorcery in it, I'm not going to lie. We're going to dip into some x86 assembler. We're not going to go too far into it in this video. In fact, this is the only point which we're really going to talk about it. But basically, this is just showing that we can. Not necessarily that we should, but that we can get as low as we need to with C. We can go all the way down to assembly directly in our code. I've seen some other C compilers that had a better way of handling assembler code in line. You have to encapsulate everything in quotes, but it's okay. Now see, this video I'm recording on Windows, but I wrote the code, the repo in a Unix environment using a different tool chain. So it'll be interesting to see if I can compile it using the Visual Studio tool chain here with IntelliJ. It detected the Visual Studio toolchain automatically when installing as a valid C and C++ toolchain, so I'll go with it. Alright, so we will talk about the inline assembler later. now we have our main function. This is our actual program. You see a little green arrow. This means IntelliJ will actually let us click this. Let me see. I wonder if you guys can see the menu on the screen that popped up. Anyways, we can click on this green arrow and a menu will pop up. We can run it. And basically, behind the scenes, IntelliJ will grab all the source files and it will build the application and then run it. So we can see here a function named main, and it has a return type of int. So basically, standard in C is your main function has to return an integer code. And this is a convention in the Unix world, not really so much in the Windows world. But in the Unix world, you typically want to have a status code, and 0 is success. Anything else means error. And what that error is dependent upon the application developer, right? So you get to decide what your error codes mean. But typically returning 0 means no errors occurred and you're done with your program. So like I said, C is very low level compared to some other languages we're going to be exploring here. And you may be asking yourself, hey Ray, why are we doing any C whatsoever? Well, the fact of the matter is C is still a very popular choice for doing high-speed computing. And like very, very high-speed computing in large-scale clusters, high-performance computing clusters, right? So, anyway, we have our main function here, returns an integer. We're going to do a couple of things. We're going to print hello world, pretty standard. It's the canonical example, pretty much in every programming language. Say hello. We're going to initialize a data structure of the type user. We're going to say user, that's the type. Remember, we lead with our types here in C. My user, that's the name of our variable, equals. We have a member of our structure called an ID. We'll give it a 0. And we have a name. And we'll call that name Susie Programmer. Why? Well, I like female names or lady names or girly names or whatever kind of names you want to call them. And I don't like writing code to Bob. You know, nothing against Bob. I'd rather talk to Susie. So anyway, we're going to do a little more work here. We're going to print the user ID and the user name. You'll notice, hey, what's this, %ID, \n. Well, in C, we need to do some escaping in our strings. This D means we're going to pass in a number, basically, and ID is a number. We see up here, ID equals 0, that ID is a number, and that's what we're going to print. And over here we have a string, myuser.name, and we're going to do a little logic here. So we're going to say if myuser.name is equal to Susie Programmer, let's go ahead and print hello myuser.name. And then we'll call our wacky crazy inline assembly demo, and then we'll be done. So let's see if it will build. This is the fun part. I've never tried to build this code on Windows. I've built it so many times on Unix and Linux. So let's see if it builds. I'm only half confident. If this were Java, I would have pretty much full confidence that it build. Oh, we can't build it. Why not? Oh, I know why. What if we just do, if we comment out our inline demo? See, that's another thing too. I was using GCC style inline assembler, and I'm trying to compile this with Microsoft Visual C and C++ compiler. So that's really not going to work. I'm not surprised there. Let's see if this will build. Oh, yep, look at that. Look at that. See that? How did I know? Oh, just a little bit of experience. So why don't we go ahead and run our demo now. And we can see hello world, my ID, my user.id, my user.name, Susie Programmer. Bada bing, bada boom. There you go. Oh, did I lean out of frame here? Bada bing, bada boom. Basic C app, right? Very tiny little piece of software. Nothing too exotic, nothing too crazy. At least not anymore. We'll make another version in Linux, or we get the inline assembler to work, and we'll make another video coming back to Windows, where we'll do some compiler preprocessor directives to determine if we're on Windows or Unix, and that'll determine how we define our inline demo function, right? And the last thing there's two more things we need to take a look at. One is user.c. Very simple here. We're just going to define we're going to do a type def for our structure called user. And for reasons I don't want to go into right now in this video, I have found that this seems to be the best way to define data structures. Meaning with the type def, the struct, and the token at the end, and the alias, whatever they want to call it at the end. Basically, I found that this is a pretty easy way to define your data structures inside of different modules, like this user module, and then being able to call that user module by including its package, and then being able to very easily create a struct this way is very convenient. Now, a lesson for another video will be the difference between making a struct this way and allocating it on the stack, right? Directly, like this is initialized as part of the compilation of the program. This is not dynamic data. This is statically baked into the software, right? So when this compiles, if I compile this on Windows every time with the same compiler, if I were to disassemble this application, I should always be able to find this piece of code in assembler form at the same location, I would think. And we can test my assumptions later in more advanced videos. Okay? But yeah, that's pretty much it. And then we'll take a look at the secret sauce that makes modern C development so easy. This is really it right here, ladies and gentlemen. CMake list.txt. Okay? Basically, CMake is a tool. Without getting too arcane on you, CMake is a tool that pretty much automates the creation of make files. Now, if you don't know anything about C programming, or why most people get away from it when they can, building applications from C source files is very laborious. Okay, basically, you have to take all of the .c and .h files, all the .c files and all their header files, and you have to compile them individually into .o files or .object files, right? Or not O, but I guess you call them object. They're not object in the sense of like object-oriented programming, more just like objects in the sense of like, here's a binary blob of instruction. So that's a real low-level concept, not the same as object-oriented programming, but an object nonetheless. Anyway, so you'd basically take all these individual tiny files, compile them one by one, and then run them through a linker. And the linker would take each of these binary blobs and assemble them piece by piece into the working software, right? So basically, I can keep adding packages. Here's the beauty of it. I can add another package called doodad, right next to user. Make a doodad struct, use it in main. I will never have to touch my CMake list.txt, right? Because I'm globbing recursively all the as sources. I'll make a variable called sources in the environment, and everything at source and underneath it that ends in .c gets globbed in here. So yeah, we might have to adjust that to add headers, but for now this works just fine. And then we can see, okay, so go from the top. We have CMake minimum version. We're finding a project called C99 Demo 01, the C language. We're going to set our CMake C standard to C99. Like I said, we're going to recursively glob through all of the C files that live underneath the source folder. We're going to add ourselves a library to be compiled in called user. And that user package, or that user library, is defined inside of our sources right here on the left, like we talked about. and then we're going to make our executable, our main entry point, the actual point where you launch the application is going to be located inside of our main.c. Right? And that's it. That's everything. That's the walkthrough of a basic C app using some modern tooling. You know, we're in under 20 minutes. We've explored a lot. And, you know, you can take these simple building blocks and start making real applications, you know. That's the beauty of main.c over here, is I've included some interesting things. You know, we've included some standard libraries. We've included our own user-defined libraries. We've made our own functions. We've called them. We've made our own data structures. And we've used them, passed them to other functions, and we've even introduced some control structures using our if block, right? So, I mean, using just those basic elements, there's a lot of software that we can compose using just that functionality. And that's the beauty of software development, because we're not actually learning C here, we're actually learning about development in general. It's just that C is very precise and very terse, you know, and you get exactly what you ask for. So, in a way, it's very unforgiving, but it's very good as one of the first languages to learn, because you know, you have to be precise. If you like for example, if I miss this semicolon right here, like line 64, if you don't see it on the screen right here, if I take this, delete the semicolon, right, and then try to run this again, the compiler is going to fail. See? There's no room for error, which is good because you want the compiler to do the hard work of like proofreading your code for you, right? In a mechanical sense, like it's not going to get your logic right, but it will get your syntax. It'll validate that, you know. And of course, there are tools called linters, which are basically style checkers. They can sometimes enforce styles. I mean, basically, it can validate that the code is well valid or syntactically correct. Even some languages have linters that can validate whether certain pieces of logic are correct or will, you know, maybe run to different types of bugs. I mean, there's all sorts of wonderful tooling out there. We've been developing software for a long time. So, anyway, still, it's a lot of info, and we're still clocking in under 20 minutes. So, thank you for tuning in. This is just a short video. So, go check out CLion, and you can find this code online on my GitHub account, on my personal GitHub account. I'll put the link below in the video, so go ahead, check it out. Subscribe to the channel, like the video, maybe give me a star on GitHub if you like the repo. This has been informative. Thanks for your time. We'll talk to you later. Bye for now.